All right, hello everybody. Welcome back. We'll continue with our notes. Our announcements are that the next Achieve homework, I'll post that later today, and that will be due Monday. Our first exam is Friday, so it's Unit Exam 1. That will cover chapters 11 and 12, but not all of 12 because we won't finish it today, but it will go through vapor pressure, which we will end with today. It will be about 14 multiple choice, 3 short answer. And anything that we covered in 11 and 12 can be on it, except for one or two things that I will not ask you to do. One is to draw a molecular orbital diagram. So like starting with atomic orbitals and combining them to form molecular orbitals. I won't ask you to do that process, but you should be able to fill in electrons for one that's provided given the atoms, or calculate bond order, or determine what a sigma or pi bond are, things like that. Another thing I will not ask is for you to determine, remember how for second period elements, some of the 2p orbital overlap has pi orbitals lower energy than sigma, and the other one has sigma orbitals lower energy than pi. You won't have to determine which atoms apply to which one. So any MO diagrams will be provided, but you should be able to do like bond order and label pi, and maybe even label like bonding orbitals and anti-bonding orbitals. You should know, bond order, like I said, things like that. I think that's all, yeah. Will there be learning checks for these two? What do you mean?
Last semester you had
Oh, the learning curves. Yeah, I can post those. I'll post those today. Yeah, thanks for reminding me. Yeah.
Is the technical curve going to be like due before the exam, or?
No, it'll be due after. They'll both be due after, because I don't want you all like stressing about finishing them before. I want you to use it as a resource, so they'll be due after. Yeah. And we won't finish chapter 12. I don't know if we'll finish it on Wednesday even. Okay, so we're going to continue with these notes. Remember this diagram that we filled out? We have 3 pictures to represent particles. One is gas, one is solid, one is liquid. And then we labeled the processes of going from solid to liquid, or vice versa, liquid to gas, vice versa, and solid to gas. Until the next slide, we're labeling which of these require energy and which release energy. So maybe just think for a second, or for a few seconds, about the previous slide. Think about for which processes do you need to add heat, and for which processes do you remove heat, or is heat released? I'll give you all a little bit of time to get started, and then we will list them. So remember that going from a lower energy state to a higher energy state requires energy. The lowest energy state is solid, and then liquid, and then gas. So starting at a solid going to a liquid, or melting, requires energy. If you're trying to melt something, it needs to be warmed up. It needs to absorb energy for that to occur. Also, if you're going from a liquid, if a substance is going from a liquid to a gas, like boiling, you have to add heat or add energy for a substance to boil, or vaporization. And then the last is going from a solid to a gas, so sublimation. Gas is higher energy state than a solid, so that change in phase would require energy. And then the rest release energy. So starting from a liquid, converting or changing phase to a solid, That solid is a lower energy phase. So to go from liquid to solid, that substance releases energy. So that will be freezing. Gas to liquid, condensation is releasing energy. And then gas to solid, deposition, also releases energy. So we have terms to describe these phase changes in the energy required for a phase change to occur. So do me a favor first, and the arrow on the left from solid to gas, switch the direction. So it should point towards the gas, because we're going to define delta H of sublimation. So that's that process of going from solid to gas. That's why we wanted to switch the arrow direction. Delta H of sublimation is termed enthalpy of sublimation, or heat of sublimation. These are two phrases that are referring to the same thing. Enthalpy of sublimation or heat of sublimation. And what this is, or defined as, is the energy required for a substance to sublime or sublimate. So for a certain amount of a specific substance, some amount of energy is required for that substance to go from a solid to a gas. If the substance is starting as a gas and becoming a solid that's releasing energy, and you would use heat of sublimation but give it a negative sign because it's the opposite phase change. For liquid to gas, remember this is vaporization. We have enthalpy, delta H, of vaporization. Sometimes called heat of vaporization. I will be using both phrases. And this is energy required for a substance to vaporize. Starting as a liquid, vaporizing into a gas, some amount of energy that is defined. We will have defined values for a specific substance to go from a liquid to a gas, so vaporize. That's enthalpy of vaporization. And then lastly, remember, solid to liquid is melting, or also called fusing. So we have heat of fusion or enthalpy of fusion. Energy required for a substance to melt. Okay, so for any substance, it will have its values for heat of fusion. They're usually in values of kilojoules per mole or kilojoules per gram. It will have a heat of vaporization value and a heat of sublimation value. So the next slide, we have values for water. These are for water at 1 atm. So different pressures, different atmospheric pressures can result different energies required for a substance to vaporize or melt or sublimate. So for water, the heat of vaporization is 40.7 kilojoules per mole. Heat of fusion is 6.01 kilojoules per mole. Enthalpy, you might remember from last term, is a path function, which means if we're looking for heat of sublimation going from a solid to vapor, we can add together the heat of fusion, solid to liquid, and heat of vaporization, liquid to gas. And the sum of those two would give us heat of sublimation. So typically, if you have a reference table, it will provide heat of fusion and heat of vaporization. It may not provide heat of sublimation, but you can always calculate that by adding these two together. So it doesn't matter how you go from solid to vapor. If you go directly or become a liquid, if the substance becomes a liquid first, the same amount of energy is required for that process. That's what it means to be a path function. So delta H of sublimation for water or for any substance is delta H of fusion plus delta H of vaporization. And for water, we use water values. So 40.7 kilojoules per mole plus 6.01 kilojoules per mole. So for water at 1 atmosphere, heat of sublimation is 46.71 kilojoules per mole. Now this is all for water, but the actual heat of vaporization, fusion, sublimation for a substance depends on what that substance is. This is all related to intermolecular forces. A liquid with stronger intermolecular forces will require more energy to vaporize. So different substances will have different heats of vaporization and fusion. So there are some examples here. The boiling point, so at what temperature the substance goes from a liquid to a gas is provided, and then also the energy required for 1 mole of that substance to vaporize at this temperature. And then same thing for melting point and then amount of energy required for 1 mole of that substance to melt. So purpose of this slide is to show you we have different values for different substances. So let's do a practice problem. We will calculate the energy required to melt 18.9 grams of ice at 0 degrees Celsius. So there is a sample of ice. We have the amount of ice present. It's at 0 degrees Celsius, which is important because that is the melting point of water. So that ice will melt at 0 degrees Celsius. Melting point and freezing point are the same temperature. And we need to know how much energy is required to melt that amount of ice. Well, we can use, which value should we use here? Fusion, yeah, we're using the heat of fusion because we're going from solid to liquid. Heat of fusion of water is 6.01 kilojoules per mole of water. So then how can we find the amount of energy, or kilojoules, required to melt 18.9 grams? There we go. We are taking the mass of water, we need to convert it to moles of water. Then we can just multiply by the heat of fusion, and we'll get kilojoules. So if we start with 18.9 grams of water times the molar mass which is 18.02 grams per mole. With this equation, we're canceling out grams of H2O. We've converted to moles of H2O. Then we can multiply by the heat of fusion, 6.01 kilojoules of energy per 1 mole of H2O. We cancel out moles of H2O, and we're left with units of kilojoules. Now, if we put this into an equation, we'll be using Q for energy. So we can say Q equals N times delta H. N is number of moles. Delta H for this, in this case, is heat of fusion in kilojoules per mole. We'll do another example where this is provided in kilojoules per gram, and we would multiply by the mass. Questions here?
So like, what is the temperature for? Why they divide it?
Because, so that is telling you that that sample is at the melting point. So if the sample is not at the melting point, then the sample has to first, let's say it was colder, it was like -10. Then that sample of ice needs to first absorb some amount of energy to increase temperature to 0 degrees, and then absorb some amount of energy to convert from solid to liquid. We're going to do that in the next slide. Okay, so this question, like I just said, tells us this sample is already at the melting point. But if we are not starting at a phase change temperature, then we will use specific heat capacity, you might recall from last term. So specific heat capacity is used when the temperature of a substance is changing, either becoming colder or warmer. And this is the amount of energy that must be added to a substance to increase its temperature by 1 degree Celsius, or the amount of energy released by a substance to decrease its temperature by 1 degree Celsius. And specific heat capacity is defined for different substances. Here I have water as a solid, water as a liquid, and water as a gas. And then the values, if we are using per gram degree Celsius or per mole degree Celsius.
Would these be provided for us?
Yeah. No, they'll be provided if you need them. So for solid water, if you're working through an equation in units of mass, so you have gram amounts, then you use 2.087 joules are required to increase the temperature of 1 gram of water by 1 degree Celsius. 37.6 joules are required to increase the temperature of ice, of 1 mole of ice, by 1 degree Celsius. If you're working with liquid water, then you use these values, or gaseous water, water vapor, you use those. And we use the same equation as last term. So we have MC delta T, Q is heat change in joules. M is the mass. C is the heat capacity. And delta T is change in temperature. And just like before, we define this as the final temperature minus the initial temperature.
Do you convert the temperature to
You could do Celsius or Kelvin here because 1 unit change in Celsius is equal to 1 unit change in Kelvin. Like 1 degree difference is the same amount, but you can't use Fahrenheit here. But you'll notice that these are in units per degree Celsius, so it's helpful to keep your delta T in degrees Celsius to cancel out. Okay, so if you are changing, or if a substance is changing temperature, then the amount of energy absorbed to change its temperature by a degree, we can define that or determine that with a specific heat capacity. But it also requires a substance, or also requires energy for a substance to convert phases, to change phases from solid to liquid or liquid to gas. Vice versa, going gas to liquid or liquid to solid would release energy. But we'll just work in terms of increasing energy. And so for a substance, each substance has a heating curve. This is for a pure substance, so no mixture. This is a graph to show how temperature changes as heat is added. So we have temperature change on the y-axis, heat being added on the x. This is the heating curve for water. So if we just look down here, we're starting, if the substance is starting at about negative 20 degrees Celsius, what form is H2O in here?
Solid.
It's a solid, it's an ice, it's ice. So heat is being added, the temperature is increasing until it reaches 0 degrees Celsius. So what's happening here at this horizontal line?
Melting.
Melting, any other ideas? Okay, just checking. It is melting. So the energy that's being added once the substance absorbs enough energy to be at 0 degrees, more heat is required for that phase change to occur. So heat is used to change to a liquid, and once that sample is completely a liquid, more heat is being added. Liquid water is absorbing energy, increasing in temperature until it reaches its boiling point. And then energy that's added is used to convert that liquid sample to a vapor. Then once the whole sample is a vapor, more heat added increases the temperature of the vapor. So that's a heating curve. This is for water because the freezing point is at 0 and the melting, or the vaporization boiling point is at 100. If you have a different substance, its freezing point and melting point will be at different values, but the general shape of the curve is the same. So let's add some labels in here. First, we have warming. Of the solid, that is this positive slope right here, negative 20 to 0. This is warming of the solid. So we're increasing temperature going left to right on the graph. This horizontal slope, slope of 0, is melting. So that substance was warmed until the melting point, then it melts. Then once everything is a liquid, that whole sample is a liquid, the next positive slope is warming of the liquid. So energy that is added is used to warm the liquid until it reaches its boiling point, and then we have boiling occur, or vaporization. Then once the entire sample is vaporized, the additional heat that's added goes towards warming the vapor. So in each of these sections, if you're increasing the temperature, we need to use Q equals MC delta T. the temperature is staying the same, but we're changing phase. We use a heat of, in this case, fusion. Temperature is changing, we use Q equals MC delta T. Phase changing, delta H of vaporization. Temperature changing, Q equals MC delta T. So we're going to do an example on the next slide where we have to consider multiple processes. We ready? Other questions? All right, let's do it. So this question here, we have a 15-gram sample of ice that is at negative 13 degrees Celsius. We are calculating the amount of energy required to melt that sample to become a liquid that is at 39 degrees Celsius. So our first step, we have to consider where the sample is starting. The sample is starting at negative 13 degrees Celsius. Well, at negative 13, we're assuming 1 atmosphere of pressure. That sample cannot melt. We can't use heat of fusion yet because that sample is not at the melting point. First, the solid has to absorb some amount of energy to reach 0 degrees Celsius. So step 1, we'll have 4 steps here. 1 is increase the temperature of ice. 2, its melting point, which is 0 degrees Celsius. Remember, if you use a different substance, if the question is about something else, not water, its melting point will be a different value. So what equation do we use here? Maybe tell the person next to you what you think. All right, what do you think? What do you all say?
Q equals MC.
Yeah, Q equals MC delta T. Did anyone else say something different? See your hand raising and then going back down. Okay, we are changing temperature from negative 13 to 0 degrees Celsius. We need to use Q equals MC delta T. Remember, M is mass, 15 grams. C is specific heat. What value are we using here? 4.184. Other ideas? 2.087. Why 2.087? Because it starts at a solid. Because it's a solid, yeah. So depending on what phase your sample is in, you use a different specific heat. So because the sample is a solid, we need to use the specific heat for the solid water, and we're going to use units of joules per gram degree Celsius because we have mass in grams. There's no need to complicate it and use mole because grams is also provided. So our C specific heat here is 2.087 joules per gram degree Celsius. And then delta T, we do final, so 0 degrees Celsius, minus initial, which is negative 13 degrees Celsius. Subtracting a negative is just adding that value. So delta T is equal to 13 here. So if you take 13, multiply by the specific heat, multiply by the mass, we have 406.965 joules. So that's the amount of energy required to raise the temperature of 15 grams of water from negative 13 to 0 degrees Celsius. So that's part 1. We've reached the melting point of water. We can't increase the temperature yet. We need to know how much energy is required for that phase change to go from a solid to a liquid. It remains at 0 degrees Celsius, but some amount of energy will be required to melt that sample. So our next step is to melt the solid at 0 degrees Celsius, or the melting point. What equation do we use here? Or what value do we use?
Is it just the value?
Yeah, one of the values that are on the slide. Yes. So we are melting the solid, so we'll use delta H of fusion. Notice that this is provided in joules per gram. When we looked at delta H of fusion for water on a previous slide, it was kilojoules per mole. I provided it in joules per gram to make this problem a little bit easier. We can multiply that value by the amount of mass, 15 grams, and that will tell us how many joules are required to melt 15 grams of solid water. So I'll use Q equals M delta H fusion. M is the mass, 15 grams. Delta H fusion is provided for you, 334 joules per gram. This is 5,010 joules. Okay, so let's think of what we've done so far. We started with negative 13 degree ice, warmed it to 0 degrees because that's the melting point, and that required 406 joules of energy. Then at 0 degrees, we've now added enough energy to melt that sample. That required 5,010 joules. But that sample is a liquid, but it's still at 0 degrees. So we need to now calculate the amount of energy required to increase the temperature to 39 degrees Celsius. So we're changing temperature. We use Q equals MC delta T. We have liquid water, so now we'll use the 4.184. Since we are working with liquid H2O, so specific heat, 4.184 joules per gram degrees Celsius. Temperature change, final minus initial, 39 degrees Celsius minus 0 degrees Celsius. All right. So now we've taken that sample that was a liquid at 0 degrees and calculated the amount of energy required to increase that temperature to 39 degrees. Are we done? What's left? Yes. We have to add everything together. We're done calculating any amounts of energy required for any change. We don't need heat of vaporization, which is on the slide as a distraction because we're not vaporizing anything. All we need to do at this point is add these together. So step 4, add all values. Now notice in this question, all of our energy values are in joules. You may have a question where heat of fusion, that's often provided in kilojoules. So your answer would be in kilojoules, and you'd have to convert that to joules to actually add everything together. So just keep that in mind for future problems. But we're adding all values, so we have 406.965 joules plus 5,010 joules plus 2,447.64 joules. Add all those together, we have 7,864.605 joules. We could convert this to kilojoules, 7.864, just dividing by 1,000. You'll be told if you need joules or kilojoules or whatnot. So that's the total amount of energy to take a 15-gram sample of ice, convert it to liquid at 39 degrees Celsius. You'll have an example of this in your homework. We don't have it in our notes. But if the sample's starting as a liquid and then going to a solid, or starting as a gas and going to a liquid, remember that process releases energy. So your Q equals MC delta T. The delta T calculation will be negative, so you'll automatically get negative values for temperature changes. But for phase changes, you have to remember to change the sign of the heat of fusion or heat of vaporization. For this case, we went from a solid to a liquid, so we use positive that requires energy. If you're doing a question where the sample goes from a liquid to a solid, that releases energy, so you just need to make that negative. Okay, other questions?
Then it would be written as fusion.
It would be like negative heat of, so yeah, it's still defined as heat of fusion, but you'd use negative heat of fusion. I understand it's a different phase change. It's freezing, but if you look at a table with these values provided, they just provide heat of fusion or heat of vaporization. All right, we will move to the next section where we'll talk about vapor pressure, boiling point, and the Clausius-Clapeyron equation. Clausius-Clapeyron equation, we'll get to that on Wednesday. That will not be on unit exam 1, but vapor pressure and boiling point will be. So vapor pressure, this is the pressure of a vapor in contact with its liquid. I want to add a note here. A substance boils when its vapor pressure, so the pressure of a vapor in contact with the liquid, is equal to atmospheric pressure. When those two pressures are equal, the substance will boil. So boiling point is when VP, short for vapor pressure, equals atmospheric pressure. All right, let's talk about what vapor pressure is. So if we look at this first beaker, this is a sample of pure water. You have a beaker with liquid water in it. This is showing the particles, liquid water, particle picture. Within that flask, some water molecules have sufficient energy to evaporate, vaporize, and become a vapor. And at the same time, other vapor molecules of water are losing energy and are becoming a liquid. So they're doing a phase change that's happening constantly in any liquid sample. So with any sample, you have your liquid, that's what we can see, but there are also some vapor particles right above at the surface of the liquid. And remember when we talked about temperature? Temperature is a measure of a substance's average kinetic energy. So that's what this diagram is showing you here. We have kinetic energy on the x-axis. If a temperature is measured at 300 Kelvin, most of the particles have a kinetic energy that's related to the temperature of 300 Kelvin, but some of the particles have higher energy. Remember, temperature is an average. So some particles have higher energy, some have enough energy to become a vapor. As you add heat to a liquid sample, you're giving it more energy, more particles have enough energy to vaporize, and then eventually everything will vaporize once it has a vapor pressure equal to atmospheric pressure. But even at room temperature, this is occurring. You have liquid molecules becoming a gas, gaseous molecules losing energy and becoming a liquid. Notice here we have a solution. Some of the non-water particles are blocking the surface, and so fewer gaseous molecules are vaporizing. So this has a lower vapor pressure than pure water. But in general, more volatile substances, so volatile means it vaporizes easier. So more volatile substances vaporize easier. Which means they have more gas phase molecules So they have more gas phase molecules above the surface of the liquid, which means they have a higher vapor pressure. Now this picture shows a flask with a water sample with a stopper on the top, so no gas molecules can escape. But if you did not have the stopper, you have some water in a glass and a beaker, some of the water molecules becoming a gas might have enough energy to escape the flask, and then they're not condensing back down into the liquid. And over time, the water will slowly evaporate until there's nothing left. But with a closed system, it will have some amount of vapor pressure constant in it. So let's think real quick. Maybe think to yourselves for a little bit and then talk with someone around you. How does vapor pressure relate to intermolecular forces? And then also think about boiling point, how intermolecular forces or vapor pressure relate to boiling point. All right, what do we think? If we have stronger intermolecular forces, what does that mean about vapor pressure of that substance?
Would it be lower because like the molecules don't like escape as easily?
Okay, so question, would it be lower because the molecules don't escape as easily? Or what else did you say?
would be higher. It's harder to break the bond.
It's higher because it's harder to break the bonds. Okay.
I said the opposite, it was, or it would be easier to vaporize more because it has more energy because the bonds are stronger.
Okay. I like hearing all of your ideas. So each of you have some correct parts of your explanation. Something with stronger intermolecular forces would require more energy for the intermolecular forces to break and become a gas. So that means something with stronger intermolecular forces, those liquid molecules are held closer and they're less likely to vaporize, and that results in a lower vapor pressure. So stronger intermolecular forces, liquid molecules are held closer together, held stronger. That means fewer gaseous molecules, meaning lower vapor pressure. So stronger intermolecular forces, lower vapor pressure. Stronger intermolecular forces also means more energy is required for that substance to become a vapor, which means you have a higher boiling point. More energy is required for that substance to release enough particles to change into the gas phase for that vapor pressure to equal atmospheric pressure, and that's when it boils. Okay, with that in mind, let's do this learning check. I will start the iClicker so you can get into it, but I recommend completing it on your slide before answering the questions because the questions are in a slightly different format. So we have 3 molecules here, butane, acetic acid, and 2-propanol. And your task is to determine which of these have the lowest vapor pressure, which one has the highest, and then there will be one that's in the middle. Now once you arrange them, add an arrow to show where the substance with the lowest boiling point is and the highest boiling point. One thing to keep in mind is that some molecules can hydrogen bond at more than one location. And having more locations where hydrogen bonding can occur results in stronger intermolecular forces. So the greater number of hydrogen bonding interactions, the stronger intermolecular force between the molecules. On the computer, if you log in on your phone, that has been working better. Yeah, because and you might just be able to go to the website. Oh, just because it has. But I think phone location is something quicker. Try phone up. So this slide, the next slide is about paper pressure. Yeah, that's.
Hey, let me know if you figure out. I'm reading off of it. Yeah. So you kind of just like. Okay, and then.
So here, the nitrogen has 3 electrons. Yeah, so they make the sigma, they also make a pi bond. Okay, so there's a total of 6, 3 here, 2 here. So I would divide. Wait.
So just kind of add them. And it's for academic. Like,
Yep, the process will be the same. Okay, so.
thank you so much.
Yeah. Yeah, I have, yeah, I want to take it down there. Yeah, we're gonna do that.
Oh, lunch time.
Okay. Yeah. Yeah, because I'm like going over the stuff, I'm like, man, so much to study in 2 days. Thanks a lot. Thank you.
Yep, no problem.